At rest, there are 10 times more sodium ions outside of the neuron than inside. There are also many chloride, phosphate, and sulfite ions that are all negatively charged inside the neuron, and there are very few negatively charged ions outside of the cell. There are also negatively charged proteins inside the cell that are too large to pass through the membrane. Depolarization occurs when a stimulus reaches a dendrite. The stimulus triggers sodium channels to open, and sodium rushes in. The sodium that rushes in causes the charge to change from negative to positive, which opens voltage-gated sodium channels, allowing more sodium to rush in. The flow of sodium into the neuron causes the localized region to change from negative to positive. It is important to note that sodium channels do not open under the myelin sheaths, therefore they only open in the nodes of Ranvier, allowing the action potential to travel much faster down the axon. Shortly after depolarization occurs, sodium channels close and potassium channels open, allowing potassium to flow out of the cell. This results in a negative charge inside the neuron and a positive charge outside of the neuron, restoring the resting potential. The flow of sodium into the end bulb opens calcium channels, allowing calcium to rush in. The flow of calcium into the end bulb causes the synaptic vesicles to travel to the bottom and release their neurotransmitters across the synapse to the next dendrite, transferring the nerve impulse. After repolarization occurs, there is more sodium inside the neuron and more potassium outside the neuron. To restore the resting potential, the sodium-potassium pumps pump 3 sodium out of the neuron for every 2 potassium that go in, restoring the original concentrations of the 2 ions.